Hello everyone, in this video we'll be discussing the exam 3 review for intermediate algebra, and let's just start off with number 1. We want to simplify these fractions. These types of fractions of polynomials in the top and bottom are referred to as rational expressions. So what we're going to do is we're going to try to factor top and bottom and then cancel, because of course with canceling fractions you cancel a common factor, right? That's how you, for example, just to kind of show you, 9 over 6, if you divide top and bottom by 3, this reduces to the fraction 3 over 2. What we're really doing is factoring 9 on top as 3 times 3, and then 6 on the bottom as 3 times 2. So then these cancel and we get 3 over 2. So that's kind of the idea here, is we want to play the same game with these three, but since they're polynomials on top and bottom, well, we have to see what that factoring entails, and it's a little complicated for some of them, specifically this one, as we'll see shortly, but let's just go in order. So here on the top I can see that you can pull an x out. And we're going to notice something that's actually a pretty common theme here. And here, the top is easier to factor than the bottom was. In fact, I haven't even talked about factoring the bottom yet, but let me say this. Since the bottom here is a trinomial, a quadratic trinomial, it'll factor as x plus something and x plus something else, possibly minuses. So we're expected to get something like this. Now I'll write x minus just as kind of a default, but that's just kind of how I do it. Now in this case, negative times negative is positive, so it will indeed be x minus x minus. But I always write it like this, and if it's plus, I'll change it to plus as I go on. But what I'll notice is, in order for this to factor in a significant way, for this to actually cancel, one of these must be 12, in order for that x minus 12 to cancel. And if that was the case, then since this is 60, the other guy here must be 5, because 12 times 5 is 60. And in fact, if you FOIL this out, you have x squared. The middle two terms will indeed combine to negative 17x, but allow you to check that on your own. And the last term, of course, is positive 60. And of course, if you want to factor kind of the old-fashioned way, what two numbers multiply to 60 and add to negative 17, negative 5, and negative 12 definitely do the trick. And again, if that one's kind of hard because 60 is pretty factorable, the fact that the top has x minus 12 as a factor is a hint that if the bottom were to factor in a significant way to cancel, then it would be this. And if it's not the case, then who cares about factoring the bottom, because it wouldn't reduce anyways. So kind of something to keep in mind. But in this case, they do indeed cancel. And we get x times, well, not x times, but x over x minus 5. And that's it. And common misconception is that the x's cancel and the x's do not cancel here. You can only cancel a factor, not a term. Okay? Okay, so that was actually pretty short. We didn't need that much space, actually. Here, these are actually way harder to factor. I'm going to take advantage of the AC method. I'm going to use the one with the smaller numbers. So I'm going to do the bottom first. So for the AC method, I'm going to multiply the outer two terms. That's what we call A and C, ax squared plus bx plus c. So a times c is 3 times 6, which is 18. And we're multiplying to that and adding to the middle one, which is 19. And of course, numbers that obviously make this happen are 1 and 18. So 1 and 18 both multiply to 18 and also add to 19. So if you want to split the middle one up as 1x plus 18x and then factor by grouping, you can certainly do that, but there's actually the shortcut where you can draw a line through this, and the front number, that's the quadratic term without the square part, is just 3x. And then if you treat these as fractions and reduce them, you'll notice that this one doesn't reduce, this one does if you divide top and bottom by 3 to x over 6. And what these actually correspond to are the factors. So the bottom will factor as 3x plus 1 and x plus 6. So these just correspond to the parts of each of these factors. And obviously, since everything is positive, we already checked the sign here, so that's fine. Otherwise, if you have some negatives, then you have to kind of make sure those signs correspond. But here, everything's positive, so we're good. Now, what does it tell us about the top? Well, it either tells us that x plus 6 is a factor or 3x plus 1 is a factor. Let's try 3x plus 1. So if 3x plus 1 is a factor, the other guy would have to be x minus 24. And that's because 1 times negative 24 will give you this negative 24 here. But I don't think this works, right? Because the middle term in this case would be 1 times x and 3 times negative 24, which is negative 72x. And those combine to negative 71x, and that's not the middle one. So what I'm really doing here is foiling and checking to see if it gives me this, and it doesn't. So that means 3x plus 1 is not our factor. So the common factor that may work is x plus 6. And if that doesn't work, then maybe there's still factors, but just in no significant way, so that there's no cancellation in the fraction. But let's see, if x plus 6 is a factor, then the other factor would have to have negative 4 as being the last term. And that's because 6 times negative 4 will give you negative 24. And because this is 3x squared, this has to be 3x, because 3x times x is 3x squared. And this works. Notice if you FOIL it out, you get 3x squared, 18x, negative 4x, 18x minus 4x is 14x, and then finally negative 24. So now these guys cancel, and we're left with 3x minus 4 over 3x plus 1, which share no common factor. Even though they look like they have the 3x in common, remember those are terms, not factors, so there's no cancellation beyond this. Great. This one's a little tricky, but I don't think it's as hard as B was. So I'm going to notice on top they have a 9 in common you can factor out. And that looks so close to 6 minus x. But if you remember this kind of difference swap action, 6 minus x is the same as negative the difference the other way around, x minus 6. And that's kind of obvious once you see the distribution. Distributing this negative gives you negative x plus 6, which is exactly this. Positive 6 and negative x. So these cancel and you actually get 9 over negative 1, which is negative 9. Now remember that when something cancels completely, there's always a 1 left in its spot. So notice when I said 1, I meant this imaginary 1 that's multiplied to x minus 6. So it's 9 over negative 1, which is negative 9. Okay, on to the next problem. Okay, so now for number 2, we're asked to perform the indicated operation, which of course we have division, addition, and then subtraction of these rational expressions. Now, one thing that's not here is multiplication, but notice division is kind of the same as multiplication. If you flip the second one, then it becomes multiplication. That's what we're going to do, but I also want to factor as we go along. So number 1 kind of set the tone for the fact that with rational expressions, you really want to factor as much as you can. So I'm going to factor top and bottom, and also simultaneously flip the second one to turn this division into a multiplication. So this 2x plus 5 on top can be factored. This can be factored quite a bit, in fact. In fact, we can pull out the smallest power of x they have in common, which is x to the third. So in doing that, these each lose 3 of their x's. So that has 1 x left for the first term, and the second one has no x's left, so that's 2x plus 5. And in fact, we see that there's straight up cancellation here. I won't write that quite yet, but I will do that in a moment. The division turns into multiplication, and now we can reciprocate this fraction, but I also want to factor. So this bottom will now be the top, and let's try to factor it. Let's see, they have the smallest power in common for their x's are x to the second. So pulling out x to the second, each of these will lose 2 of their x's. That loses 2 of its 3, so there's 7x left, because 1x. And this x squared loses all of its x's, but remember there's at least a 1 left. It's 1x squared after all. So that means this is minus 1. Okay, perfect. And the numerator, which is now the denominator, if I factor this, something to keep in mind is that these two will already cancel out. So there's really no point in me factoring this unless it will cancel with that 7x minus 1 factor. Because obviously these don't all have an x in common, so we can't factor an x out or anything like that. So that gives me a hint, kind of like we saw with question 1, that this may factor as 7x minus 1, which was that other factor. And then since 7x times 5x is 35, x squared, and that'll work, but negative 1 times positive 1 will be this negative 1, so this must be positive 1. Just kind of checking by guess and check methods of foiling. Now if you FOIL this out, you'll indeed see it works out. We get 35x squared for the first term, 7x, negative 5x, those combine to positive 2x, that's the middle one. Negative 1 times positive 1 is negative 1. And now we can see cancellation. These cancel straight up, these cancel straight up, and then beyond that there's actually some cross cancellation here. So remember the way this works is that we are basically subtracting the powers. So I know that 3 minus 1 is 2, so all of these 2 will cancel with 2 of these 3, so there's 1 left. So notice, nothing's left on top, but there's always at least a 1 in multiplication as we just spoke about. So there's a 1 here and a 1 here, but 1 times 1 is 1 on top. So altogether this is 1 all over, 1x left on the bottom, and a 5x plus 1. I'm going to leave it like that. If you want to distribute this to get 5x squared plus x, you can, but I'm just going to leave it like this. It's fine. Okay, for this one, again, I want to factor the denominators. And I'm actually going to factor them and replace the denominators with their factor versions. This one I'll hold off on, but notice that this is actually easier to factor. You can pull a 2 out and you get 2 times the quantity x plus 3. Now this is actually not too bad to factor. The two numbers that multiply to negative 3, the last one, and add to the middle positive 2 are, well, I guess it's has to be 3 and 1, positive 3 and negative 1, I think, yep. Those add to positive 2 and they multiply to negative 3. So that means this guy factors as x plus 3 times x minus 1. Right, x plus this, x plus that. But since this is negative, x plus negative 1 is x minus 1. But we'll notice that these both actually have an x plus 3 in common. And that's kind of good. It won't necessarily always happen, but it helps because there's less to multiply to each of these other ones to accomplish a least common denominator. So in this case, what we look for, it's a mouthful, okay, just bear with me. What we look for is what we need to multiply this denominator by that the other denominator has as a factor that this one doesn't have, and vice versa. So I'm going to notice this needs a 2 that this has, but this doesn't. So in other words, they share this x plus 3 factor, but this is missing a 2 that has that this doesn't have as a factor. And similarly on this side, top and bottom, we need to multiply by what this has as a factor that this doesn't have, which of course is that x minus 1 that I was pointing to just now. Now when you're multiplying, it's a quantitative thing. So we do need parentheses there. Otherwise we don't see the distribution, and it's not really multiplying 2 to the entire thing. And you may trick yourself to think it's just 2x plus 2, in which case 2 is only multiplied to the x, not to the whole x plus 2. Okay. In any event, let's continue now. So I will distribute this 2, so we get 2x plus 4. Since this is over a common denominator now, we can write plus 1 times this, but 1 times x minus 1 is just x minus 1. And now all over the common denominator, which I'll leave factored actually, 2 times x plus 3 times x minus 1. And notice the top combines 2x plus x is 3x, and 4x minus 1, or 4 minus 1, excuse me, is a positive 3. So let's see if we can squeeze it in here. So we get 3x plus 3 all over 2 times x plus 3 times x minus 1. Now if you want to notice that the top can be factored, it's a good idea to factor that out. So I'll factor the 3 out. But there's actually no point in doing that because it doesn't factor in a significant way. What do I mean by that? Well, if we pull the 3 out, we'll get x plus 1. But since that 3 wouldn't factor with any 3 factor in the bottom only has a factor of 2 as a constant, only constant factor. And x plus 1 is not any of these. If that was an x plus 1 instead of an x minus 1, then we should do it and see the cancellation. But what I'm trying to say is that since factoring this doesn't include in any cancellation, there's no point in even factoring. So you can try to factor it to see what I mean, but since there's no cancellation, the result from that, there's no point in doing that. That's all I'm saying. Okay, so same idea here, but they're just a little harder to factor. So what two numbers multiply to negative 10 and add to positive 3? Those, of course, will be 5 and 2. Those multiply to 10 and add to 3. Well, you have to change the signs of it. So positive 5 and negative 2 do the trick. 5 and 2, good. Right, so I'm going to replace this. Let me do it in blue this time. So this is w plus 5 times w minus 2. Perfect. And now this guy, what two numbers multiply to negative 15 now and add to positive 2? 15 is 5 times 3. That's what comes to mind for me. Changing the signs to make them add to this will be positive 5 and negative 3. So that's x plus 5 and x minus 3. Well, it's really w, isn't it? So that's right. W plus 5 times w minus 3. And again, they share a common factor of w plus 5, which doesn't always happen, but it's nice when it does. Okay, so I need to multiply this one top and bottom by what? Let's see if we can see it. Well, from the other one, it needs the w minus 3, so we need to multiply top and bottom by w minus 3. Perfect. Here, multiply top and bottom by the factor that this has that we don't have on this side, which is w minus 2. Now, it's also very, very, very important to notice that we have a subtraction here instead of an addition. So whatever this becomes and whatever this becomes, this negative must distribute to the second thing. So I'll actually write that out pretty carefully in the next line here. So I'm going to leave the bottom completely factored still. So let's write it like this. W plus 5, W minus 3, and W minus 2. That's what the denominator is as the least common denominator. Okay. Now on the top, I'll do this kind of quickly. You can FOIL this out, but I'm going to show you something that's kind of interesting. That for some reason this isn't like taught very often, but it's the opposite of factoring. So when you factor, you look for two things, then multiply to the last one and add to the middle one, which is what we've been doing, right? But when you have factors that don't have anything in front of the variable, like here W minus 3, W minus 9, for example, really what this will become is W squared, and then the middle term will be the sum of these two numbers. Notice negative 3 minus 9 is negative 12W, and then the product will be the last term, which is going to be positive 27. So I can tell right away this is W squared minus 12W plus 27. Now if you want to take your time and actually FOIL it out, I recommend you do that just to see it anyways, but that's a really quick way of FOILing out a pair of binomials like that. Okay? And then minus this quantity. Okay, like I was saying, the negative needs to be outside of parentheses so we can distribute the negative. Okay, that's kind of the trickier part of part C here. Now again, if you add these two numbers, negative 11 and negative 2, you get negative 13. And if you multiply them, you get positive 22. So that's going to give us W squared minus 13W plus 22. Let me squeeze it in here. Probably barely makes it on the screen. Okay, plus 22. So now if we distribute this negative and combine, what do we get up on top? Don't have too much space left, but I think we can maybe work it out. Let's see. So it's going to be all over the bottom, which again, W plus 5, W minus 3, W minus 2. Very good. And then the top, we have W squared minus W squared will cancel. Then we have negative 12W minus negative 13W. So I'm not writing the details, but that's negative 12W plus 13W because of the double negative. So that will amount to just W. And then we have 27 minus 22, which is positive 5. And look at that. We have cancellation because technically, of course, this is this times 1. Like we've been seeing, there's always an imaginary 1 left in multiplication. So that when these cancel, which didn't happen in any of the above ones after combining, but it did here. Well, it's kind of a lie. It kind of happened here in A, but that's kind of what happens when you multiply. They factor and cancel as you go along. But with addition and subtraction, it's kind of rare that it cancels after the fact. So here we get 1 over W minus 3 times W minus 2, and I'm going to leave it factored like that for the bottom. Okay, fantastic. That took a lot more time than the previous problem, but that was it. So now let's move on to number 3. All right, so now for number 3, we're asked to solve these 3 equations. It's quite a bit. Now, there's something kind of funny that happens. So when you have a fraction equals a fraction, you can always cross multiply actually. But I warn you that if you have quadratic factors, you need to be careful, and it's best to find the LCD and multiply through with the LCD instead. Because you may get something that is, it's kind of more than what's needed, I guess, is a way of putting it. But we'll see that once we hit B, because here, these are non-quadratic denominators, and they actually have nothing in common as it turns out. They can't be factored, basically. So if we just straight up cross multiply this to that side, this to this side, we end up getting the following. We end up getting 2 times the quantity x minus 9 is equal to 1 times the quantity x plus 9, which is just itself. Distributing this, we get 2x minus 18 is equal to x plus 9. Pretty easy to solve this. Subtract this x to this side, we can simultaneously add this 18 to the right. These cancel, that's 1x, so we get 27. Now, what's really required for us to do with rational equations with fractions, we must check that this doesn't result in a zero denominator. Now, if you want to actually check this, you can check any equation, right? Any solution to an equation, you can always check by plugging it in to see if it actually works. I'm not going to be doing that here. You can, and it definitely helps and is encouraged to do that. But what I'm going to do is just check that there's no zero denominator, because if there is, then this is really an extraneous solution. And that is pretty important. You want to make sure that you cross out any extraneous solutions, and you can only find out if you have an extraneous solution for these kinds of questions by checking to see if there's no zero denominator. But notice the denominator being 0 only occurs here when x is either -9 or +9. Notice, when this is 0, x is -9. When this is 0, x is +9. So this is really kind of the domain of this expression, is one way to think of it, or of each of these expressions kind of combined. So since x here is neither of those, then we're good. So it's kind of an alternative way of doing that. Instead of plugging it in directly to the denominators, I'm looking to see ahead of time what the denominators must have x values in order to be 0 are. And in this case, it's -9, but this is neither of those. Okay, great. So now for this one, this is kind of what I was talking about. So we could cross multiply, and you can do that if you want, but when you do that, you will get a quadratic equation in the end, which I don't know how necessary that is. Let's kind of take a look differently here. We can actually factor. So this factors as 4 times x plus 3, because they both can be divided by 4. And this is actually a difference of squares that you should know, x minus 3 times x plus 3. So we should have good recognition of difference of squares by now. So notice the LCD here is actually just, well, it's actually 4 times, I almost forgot the 4 in front, 4 times x minus 3 times x plus 3. Kind of from what we saw with the last problem, with B and C specifically from number 2, is you want to see what this doesn't have that has, and vice versa. But altogether you get 4 times x minus 3 times x plus 3. That would be the least common denominator, the LCD. So I want to multiply both sides by this. Now I'm not going to actually write it out because it's too much to write out. Like it'd be too long to write this twice. But what I will say is that when you multiply this side by the LCD, both of these terms will cancel, and you're only really multiplying by 4. Now again, I'm not multiplying top and bottom by this, I'm just multiplying through by this huge expression. So the x minus 3 and x plus 3 will cancel, and you'll just have the top times 4. And that's what generally happens, is when you multiply by the LCD, whatever didn't cancel with this will be multiplied to the top. So here, what doesn't cancel with this is 4, so 4 is multiplied to the top. On the other side, we get -7 multiplied by what doesn't cancel with this denominator. These two cancel, the x minus 3 doesn't. Distributing the -7, we get -7x plus 21. So that's pretty simple to solve. Subtract the 21 over. 21 minus 12 is a 9, so that's going to be -9 is equal to -7x. So that means dividing by -7, x is equal to +9 over 7. And it's pretty easy to check that this is not an extraneous solution, because here when you set the denominators each equal to 0, or at least their factors equal to 0, again, x cannot be +3 or -3. And another way of doing that actually is setting each factor and the LCD equal to 0, with the exception, of course, of the constant multiples, like 4 is never 0. Right, so back to that cross multiplying, I said you'd get a quadratic, and it's pretty easy to see that because this x squared multiplied to that -7 after distribution will be -7x squared. And there's no x squared over there, so this is a legitimate quadratic equation after cross multiplying. So if you try that on your own, move everything to one side so the zeros on the other and factor, and then set each of those factors equal to 0, you'll get 7x minus 9 for one of them, which will correspond to x equals 9 over 7, and the other factor will correspond to an extraneous solution. So that's the kind of issue with cross multiplying. And I warn you that when you cross multiply, you want to make sure that your denominators factored have nothing in common before you jump to those conclusions, or jump to that conclusion. Okay, now here, this, honestly, I don't think we have enough space, but let's try it. So I'm going to factor each of these denominators, and then I'm going to look for the LCD. So let's factor them first. I'm going to do it kind of quickly. We saw this one kind of already. The two numbers are multiplied to 15 and add to 2 or 3 and 5. Of course, they have to have opposite signs to subtract the 2. So it should be +5, -3 to make the signs work out. So there we go. This guy, let's see, the middle one here is 1. So what two numbers multiply to 12 but add to 1, or I guess have a difference of 1? That'd be 4 and 3. To make the signs work out, it should be +4 and -3. Great. And then for this one, they're both positive, so it's a plus and a plus. And 4 times 5 is 20, and 4 plus 5 is also 9. So that works. So those are the two numbers that multiply to the last and add to the middle. Great. So now what I'm going to do is I'm going to find the LCD. And again, you'll notice that a lot of these have something in common. So in fact, if you just look at each of the factors, we have an a plus 5. We have an a minus 3, which also appears here. The a plus 5 also appears there. And what this doesn't have that these two have is a plus 4, and that's it. These are all of the factors up to their power. So if you have a power, you need to include that power as well. But here the powers are 1, so they're only included once. Okay, so now what I'm going to do is, again, I'm going to see, and let's see if we can see it okay. Again, I may need to actually move back up to the top of the board here in a minute, but let's see. So I'm going to multiply each of these 3 terms, I guess you can say, by the LCD and see what doesn't cancel, and multiply the top by what doesn't cancel. Another way to see that is to multiply every term by this thing. You'll see the cross cancellation, but what won't cancel, well, is just whatever doesn't cancel, but that's multiplied to the top. And we're left now with an equation involving no denominators. So let's take a look. So here, what doesn't cancel is the a plus 4, so the top is multiplied to a plus 4. Okay, great. Here, this is 5 times what doesn't cancel. The a plus 5 doesn't cancel with the denominator, so that's multiplied to a plus 5. And then this 5 is multiplied to what didn't cancel here. That cancels, the a plus 5 cancels, so this guy doesn't cancel. Great. So maybe we don't actually need to move up. I think this is doable. So let's distribute, and let's see if we can combine things as we go along. So we get 2a plus 5a, that's 7a. We get 8, that's 2 times 4, that's 8, and then 5 times 5 is 25. Well, what's 8 plus 25? That's 33. I probably really should be writing these out, but again, just because of space, I'm not. But you know what, maybe I'll actually do it off to the side here. So we get 2a plus 8, and then we have plus 5a plus 25. So those combine to 7a, good, and these combine to 33, good. So it's good to write it out just to see that. When you distribute this 5, you get 5a negative 15. Okay, now I'm going to subtract that 5a to this side. Try to squeeze it here in the bottom. And simultaneously subtract this 33 to that side. So you get all a's on one side and all non-a's on the other. What we end up getting is 2a, right? 7a minus 5a is 2a, equals, that's going to be negative 48. Does that look right? I think that sounds about right, good. And then dividing by 2 gives you a is equal to negative 24. And I know negative 24 is not extraneous, assuming all this work is correct, of course. So we can actually plug it in and see. But again, just assuming that it's not extraneous, or assuming the work is correct, I know it's not extraneous because the only time we get a zero denominator is when one of these factors is 0, which only occurs when a is either equal to negative 5 from this factor, positive 3 from this one, and negative 4 from the last one. And that's just setting each of those equal to 0, you get those numbers as a result. So here a can't be any of those, but negative 24 isn't, so that's a legit solution. If you want to actually plug it in and see that this fraction plus that fraction is equal to that fraction when a is equal to negative 24, knock yourself out, try it. I'm not going to do it though because of time. And now let's move on to number 4. All right, so now for number 4, we have kind of a word problem. This has to do with variation and different setups of variation. Honestly, this is not a very wordy problem. This is kind of direct and straight to the point as far as the definitions of direct and inverse variation go. So here we have x and y vary directly, x and y vary inversely. Here's also inverse, but we have to deal with a different bit of wording, which we'll get to in a second. But what the question actually specifies here is that if x is 10 when y is 2, then we must find x when y is 4 if the following different cases occur. So they're separate, okay? So it's almost like alternate scenarios. So these can't all happen at the same time. So here, A, we're assuming this, B, we're assuming that, so we're kind of like an alternate universes, you can kind of imagine. So first off, what are the setups for direct and inverse variation? Well, long story short, that when you have direct variation with variables x and y, then x is equal to a constant times y. And for inverse variation, x is equal to k over y. Now, some people may think that order matters, but I'll tell you right now, with a problem like this, where you're asked to find a variable given another one with a bit of information given to you ahead of time, the order does not matter. Now, also notice here k is a constant. And that's kind of the main reason why the order doesn't matter, because if you were to multiply both sides by y and divide by x, you'll get y is equal to k over x. So for inverse variation, the order straight up doesn't matter. But here, if you divide by k, then you'll get something like y is equal to 1 over k times x, and the order technically would matter, but 1 over k is still a constant. So if you set it up the other way around, then I would set it up, for example, your constant may be different, but the value for x given y is 4 at the very end of things will be the same no matter what. So if you want to try to play around with different ordering, writing y equals k times x instead of x equals k times y, try it and you'll see that your k will be the reciprocal of my k that I'm going to get here. But the answer in the end for x when y is 4 will be the same. So the first bit of information here, x is 10 when y is 2, that's only given to find k. So let's set up first. So the direct setup is x is equal to k times y. That's the first thing. Then we use the fact that when x is 10, y must be 2. So I'm going to use that and plug it in. So that means x is 10, k we don't know, y is 2. So then dividing by 2 gives us that k must be equal to 5. 10 divided by 2 is 5. So it's pretty clear. But remember, k is a constant. What does constant mean? It means it's unchanging. K doesn't change. So in fact, this equation has k equal to 5 no matter what x and y are. So in fact, we actually know that our equation really is x is equal to 5 times y. Now again, if you were to set it up the other way, y is equal to k times x, plug these in, you'll get k is 1/5. But if x is equal to, well, if y is equal to 1/5 k, multiplied by 5, you'll get exactly this. So it's the same idea, actually. Okay, so now to find x when y is equal to 4, once we found our constant, so at this point, we're going to now let y equal 4 and figure out what x must be. And in fact, when y is equal to 4, we get right away x is equal to 5 times 4, which is 20. So that means x is equal to 20 when y is equal to 4 for that scenario, for direct variation. And of course, assuming x is 10 when y is 2. Fantastic. So now to the next one, we know inverse variation has this setup, so I'll write this out. Okay, then I'm going to use our first condition here. Let x equals 10 when y is equal to 2. Plug those values in, we get 10 is equal to k over 2. Multiply both sides by 2 here to get k by itself. We end up getting that k is 20. Right, 10 times 2 is 20. So in fact, this equation really is x is equal to 20 over y because k, our constant, is 20. So we get x is equal to 20 over y. Now, when y is 4, what is x? Well, now letting y equal 4, we get that x is equal to 20 over 4, which is 5. So x is 5 when y is 4 here. Perfect. Okay, now what about the last one? Well, the last one is inverse variation, but it says with the square of y, or varies inversely as the square of y. So what is the square of y? It's just a fancy way of saying y squared. So instead of x and y varying inversely, x and y squared vary inversely. So I'm going to write x is equal to k over y squared. And again, if you were to write it the other way around, y squared is equal to k over x. Similarly, if you were to switch this around, you'll get the exact same thing in the end. And in fact, with inverse variation, the funny thing is the setup isn't, or the constant isn't different. It's the same no matter what. But with direct variation, it turns out the constants are reciprocals when you mess with the order. Anyways, plugging in our first condition, x equals 10 when y is equal to 2, what do we get? We get 10 is equal to k over 2 squared. Notice 2 squared is 4. Multiply both sides by 4. We get k is equal to 40. So now our setup here now is x is equal to k over y squared, but our constant k we found to be 40. So with that in mind, our actual equation is x is equal to 40 over y squared. And now finally, when y is equal to 4, x is equal to 40 over 4 squared, which of course is 40 over 16. And if you reduce this by dividing top and bottom by 8, you get 5 over 2, which is the final answer and the end for question 4. Let's move on to question 5. All right, so for number 5, we're asked to simplify these radicals. And there's a few ways, honestly, to simplify a radical. But basically what you want to do is you want to factor it so that you have perfect whatever the index is. Now the index, if you don't remember, is just this little number here. So this is the third root of this thing, sometimes known as the cube root. When there's no number, then it's assumed to be 2, so we call it the square root. Notice squaring is taking things to the second power, so when you have the radical symbol with no index, it's assumed to be 2. Okay, and here this is the 12th root, so the index is 12. Now, what I want to do is I want to write each of the insides as, well, factored, and each of those factors so that they're squares, and then we can split it up and take square roots. So I'll give you an idea here. So let's just ignore this y to the 17th for a little bit. Now, if I take the square root of 64 and multiply it by the square root of x to the 8th, so here I'm using a property. So a property of radicals, you can split it up in multiplication, and that's why we want to factor things. The square root of 64, well, 64 is actually 8 squared. So you can write it like this, and the square and square root cancel, and you just get 8. And similarly, x to the 8th, since 8 is even, you can write this as x to the 4th squared, because 4 times 2 is 8, of course. So just like this cancels with this squared, this radical will cancel with this square, and we get 8 times x to the 4th. Now, it is only because these index radicals, the index of these radicals, that is 2, that the square and those cancel. So for here, when we do this, that should be a 3 canceling with this cube root, if that makes sense. So if I were to take the cube root of a to the 3rd, then these would cancel and you get 8. But notice a to the 3rd is like 512 or something, which is, not, of course, not 64. So that's something to keep in mind. Now, because of this, really what we're doing is we're looking for a repeated factor. So this is the same as, for example, the cube root of 8 times 8 times 8. So whatever the index is, you need that many of them in order to break out as 1. So that's outside of the radical now. So that's what I'm going to use. That idea is, I think, pretty important and helps people very often figure this out in kind of a simple way. But again, there's another way of doing that that I'll show as well. But let's kind of hang with that idea for a second. So if I factor this completely, well, we already know the square root of 64 is 8, so might as well just pull that out. And we already argued that that was also x to the 4th. But again, a way of seeing that is that if you square root x to the 8th, that's how many x's? A total of 8 x's. And because this index, it's one more x, sorry. Because the index is 2, we need 2 x's to break out as 1 x each. So how many pairs of x's are there? There's 4 x's, 4 pairs of x's, that is. So x to the 4th pops out. Now, with y to the 17th, we want to do something similar, but since 17 is odd, the way of thinking of it is it's going to be a bunch of y's and then 1 y left over. The reason why I'm leaving that 1 y left over is because now we can pair these off. Because since y to the 17th is an odd power of y, then it doesn't break into even pairs, even number of pairs like x to the 8th did. So if you broke one off, then you have 16 y's left over. And since there are 16 y's, then that's 8 pairs of y's. Another way of seeing this is that when you take the square root of an even power, it's the same as halving that power. And that's pretty simple to see if we understand the fact that radicals are really fraction exponents. So specifically here, since the index here is 2, we can write this whole thing as a 1/2 power. So if the index is 3, we can write that as a 1/3 power. And that idea we'll actually see here a little bit. And that helps, but again, since this is odd, there's 1 left behind in order for us to pull off this trick. So I really have to split this as the square root of y times the square root of 16, and the square root of 16 is y to the 8th. So we get a y to the 8th coming out, and the square root of y left over. Now, if that was hard to follow, there's another way of doing this that very much relies on what I just said, If it's an even power that we're taking the square root of, you just half it. But if it's an odd power, then you have one left behind, and half of one less than that amount come out. So 1 less than 17 is 16, and half of that is 8, so 8 come out. So that's a way to think of it, but again, there's a lot of different ways to think of simplifying radicals. I hope that helped. It wasn't too confusing, but we're going to see this idea a lot in these other parts. Okay, but I think I wanted to spend a lot of time on this one, so we'll kind of see it with a little less explanation and less detail with these ones. Now, this one is kind of funny because if you factor 16, no matter how you factor 16, 4 times 4, each of those 4s is 2 times 2. And if you wanted to like factor as 8 times 2 and then factor the 8 and keep going, you'll get eventually to 2 times 2 times 2 times 2. So 4 2s multiplied. And it can't break down any further because 2 is a prime number. So in fact, we actually just get 2 to the 4th, or 4 2s. But I said that we need that index amount. But here's the thing. We don't have 12 themes multiplied. We only have 4 themes multiplied. So that idea kind of doesn't work. But what comes to the rescue here is fraction powers. Now what's kind of funny is if you look through the entire exam, fraction powers aren't really mentioned, or for the review I mean. If you look at the entire review, there's no mention of any fraction powers as is. But we'll use the idea of fraction powers to make sense of some things. I spoke of it here, and here we'll definitely see it. 16 is the same as 2 to the 4th, and the 12th root is the same as the 1/12 power. So in fact, this is really the same as 2 to the 4 over 12. And notice 4 over 12 reduces to 1/3. And 1/3 is the cube root of 2. So in this case, kind of the opposite of what we saw for A, we don't have enough to pull out, we have less. So write the index as, or the radical that is, as a fraction power, factor the inside as a complete power if you can, multiply those to get a new fraction power, reduce it, rewrite it as a radical. A little complicated, but it's kind of the only thing you can do, so you're kind of forced into a corner there. Okay, so now with this one, 80 actually has no cube root, and you can see that by looking at cubes. So 1 cubed, 2 cubed, 3 cubed, 4 cubed, and then 5 cubed bypasses it. So what do I mean by bypasses it? It skips 80. So 1 cubed is 1, 2 cubed is 2 times 2 times 2, which is 4 times 2, that's 8. That's 27, this is 64, that's 125. So 80 skipped. So 80 actually has no cube root, but, or no integer cube root, I should say. But since 80 is 8 times 10, look at that, 8 has a cube root, it's 2. So we can say that the cube root of 80 is equal to the cube root of 8 times the cube root of 10. So splitting it up like this. Now 10 only factors as 2 times 5, so there's no three-peats, if you will, of any of those factors, unfortunately, so that kind of stays as is. But we know this is 2 because 2 cubed is 8. So in fact, we can do that. And look at this. If we split this up further, the cube root of x cubed is just x because it matches the power, or the index matches the power that is. Exactly. So let's use that idea here. Hope that's okay now. So this is the cube root of 80 times the cube root of x cubed. The cube root of x cubed, again, the power cancels the index radical there, so we just get an x. I'll write the x in front because this guy is the cube root of 10 times 2. So I'll write the 2 in front of x and the cube root of 10 behind that x. If you wanted to write 2 times cube root of 10 times x, you could, but generally you write the roots last just so there's no confusion what's inside the radical and what's not inside the radical. Okay, now this last one, there's a few ways of doing this. One way is to do exactly what we did here. Notice that 24 is 8 times 3. It's also 6 times 4 and 2 times 12 and 24 times 1. But 8 times 3 is the best when it comes to cube roots because we know the cube root of 8 we just found was 2. So this is actually 2 times the cube root of 3. So what that means is that if you factor the top or simplify the top as 2 cube root of 3, the denominator is cube root of 3 already and those cancel. So we're left with 2 over 1. Remember there's at least a 1 here. So our answer is just 2. Now there's of course a much better way of doing this. And the better way of doing this is to notice that we can actually write this as this whole fraction. We can write as the cube root of the top inside over the bottom inside. Now that's another I guess, property of radical is similar to splitting it up by multiplication. We can split it up by division. And notice 24 divided by 3 is 8. There we go. And this right away is 2. But regardless, we get 2 as our answer. So there we go. Great. Awesome. So that was number 5. Now let's move on to number 6. Okay, so number 6 now says to perform the following operations. If you haven't noticed already, there's kind of some similarities, I guess you can say, with the exam review, that is. So for example, we simplified for rational equations or rational expressions. Then we simplified for radicals here with number 5 before this. And then there was an operational one with rational expressions, just like there is with radicals. And then we'll shortly actually see in problem 8 a equation solving one, much like we saw with number 3. So there's a lot of parallels we can make between rational expressions and radical expressions. But right, so let's move on to this. So we're asked to multiply, add, and then take the square of this. So in fact, this is very much thought of kind of like as you would see a polynomial. So I look at this and I just think FOIL. That's kind of an obvious thing to do, I hope. It's just up to us to know how to combine radical terms, and that's just multiplying the insides when the indices are the same. But these are both square roots, so they have the same 2 index. So let's see. So that's 4 times 3, that's 12, so that's simple. And then that's 4 times negative 2 is negative 8 radical 3. So the radical remains the same. Kind of like 4 times 2x is 8x. 4 times 2 radical 3 is 8 times radical 3. So think of it like that. Okay, now we have 2 radical 5 times 3, that's 6 radical 5 in kind of a similar fashion. And now the 2 times negative 2 is negative 4 on the outside. Now radical 5 times radical 3 is radical 5 times 3, which is 15. And 15 factors is 5 times 3. There's no pair of primes there. There's no pair of factors, that is. So you can't break that radical any further or simplify it. In fact, none of these can be simplified or combined. There are no like radicals in sight. This, believe it or not, is our answer. So not as nice as what we're used to with polynomials, because we get at least some combining terms. But here, not so much. Okay. Now, speaking of like radicals are radical terms that have the same index, like here, and the same inside. So think of like adding terms or polynomials or monomials or just terms in a polynomial that have the same base and the same power. So like, for example, 4x squared y minus 3x squared y. We can combine these to 1x squared y, which is just x squared y, because they have the same powers of the same base. Indices are kind of like powers, and the insides, which are called radicands, are kind of like the base. So those must both be the same in order to combine these things. Now, at face value, it looks like they're not, but radicals can be simplified. So we saw 8 happening a lot in the last one. 16 is 2 times 8. So in fact, this is 4 times 2 times the cube root of 2. Now, if you didn't quite follow that, what I'm doing is I'm writing the cube root of 16 as a cube root of 8 times the cube root of 2. I'm only doing that and splitting it up this way because this is just 2 itself. So that's how I got that extra 2 coming out, and that's how this became a 2 on the inside. Okay, it's 8 times 2. 8 comes out of the cube root as a 2 because the cube root of 8 is 2. So all in all, this is actually 8, and I'll write it over here. 8 radical 2 for the first term. Then plus, now let's see if we can simplify this. Now, what I'll do is I'll just factor as much as I can. So I have 250. I'm not going to notice anything clever or anything like that. I'll just go through the motions. So it ends in a 0, so that means it's 10 times whatever it is without the 0. So it's 10 times 25. Let's keep factoring. 5 times 2, 5 times 5, that's it. 5 can't be factored further, neither can 2. So in fact, this is 2 times 5 times 5 times 5, so 3 5s. There we go, we have a cube. So we can write this as the cube root of 5 cubed times the cube root of 2. The cube root of 5 cubed is just 5 because the cube cancels, and the cube root of 2 is just the cube root of 2. So this term here becomes, let me write it over here, 5 times the cube root of 2. So we saw this this simplification of this radical a little differently than we saw for this one, but still they were simplified, and they simplify into like radicals now. They have the same insides with the same indices. So what we can do now is combine them by adding the coefficients. 8 plus 5 is 13, so this must be 13 radical 2 as the answer. Now, if that throws you off why we don't do anything with the insides or combine those, remember, it's very much like what happens with polynomials. So think of 8x plus 5x, it's 13x. You don't add the powers. Only when you multiply that happens. When you add, the powers must be the same, but you're only adding their coefficients, the power stays the same, much like here. Okay, now for this one, this is actually very similar to A. And it's not obvious at first, but you have to expand it out. Right? 4 minus radical 2 squared is that thing multiplied by itself. Then we can FOIL, and because these have the same insides, we'll actually get some combining of terms, unlike we had here. So let's see that with the FOIL. 4 times 4, 4 times that times 4, that times that. So 4 times 4 is 16. 4 times negative radical 2 is negative 4 radical 2. Negative radical 2 times 4 is another negative 4 radical 2. And negative radical 2 times negative radical 2 is positive. There's a few ways of seeing this. If you want to write it as positive radical 2 squared, that's a nice way of seeing that. But just like the square and radicals cancel when the square is on the inside, the square and radical also cancel when the square is on the outside. Makes no difference. And you can see that because of, I guess, fraction powers. Radical 2 is really 2 to the 1/2 and 2 to the 1/2 to the second. When you multiply those powers, you get 1. So it's just 2 to the 1. So in fact, these combine to negative 8, radical 2. And these actually also combine now because that's just a positive 2. And 2 plus 16 is 18. So we get an 18 in front. Now this is not the only way of doing this. And in fact, there's actually I think a quicker way. I mean, it's not necessary to show, but it's something that we all should know. Is that a plus b squared, a binomial squared, is always going to simplify as a squared plus 2ab plus b squared. So the chant I remember and like to tell people is that if you have a binomial square, two things added together squared, it's the first one squared plus 2 times their product plus the last one squared. You don't just square them, you get this middle term, which is 2 times their product. So if we had recognized that here, let me show you in I guess blue. We would get the first one squared, which is 16. 2 times their product, the product is negative 4 radical 2. But if you double that, you get a radical 2. And the last one squared is this squared, but that cancels this. These two combine, it's a positive, because negative radical 2 squared is negative times negative is positive, so it's positive for this last one. So these two combine to 18, so you get 18 minus 8 radical 2, which is exactly that. Great. But again, if you don't quite remember this, you don't want to risk it, I honestly understand completely if you just write it out. But don't forget to do that. Don't just distribute the 2, because that's incorrect. Okay. So moving on to number 7 now. All right, so for number 7, we're asked to rationalize the denominator. Now what rationalizing means is to make rational. Now rational basically means it's a fraction of integers, and radicals that don't break, like the square root of 15 or the square root of 2 or square root of 5, a lot of these radicals, they don't break. Like the square root of 16, for example, is just 4, so that's rational. But the square root of these weird ones that don't simplify further, those are not rational. So to rationalize a side is to make that side a non-radical term, basically. So long story short, we want to get rid of radicals in the denominator here. If you were to rationalize the numerator, it'd be the same thing, but with the numerator. Now, as it turns out, for me personally, I think A is actually the more difficult one. So when you have a denominator that is a kind of a radical binomial like this, then you would actually need to multiply top and bottom by the conjugate of the denominator, which is a sign change. So the same terms, but the sign changes. And that's actually more complicated than what we'll see with B and C, so I kind of question the order I put here, but that's okay. Now, the reason why this works is because the denominator will give you a difference of squares. Think of a minus b times a plus b, it's always a squared minus b squared. And you can FOIL it out if you want, but I'm just going to show that it's 4 squared minus 15 squared. Radical 15 squared. And remember, squaring a radical cancels it out and just gives you 15. Now, 4 squared is 16, so that's going to be 16 minus radical 15 squared. And 16 minus 15 is just 1. On the top, we can distribute this 9. Nothing special, though. We'll just get 36 plus 9 radical 15. And since this is just 1 in the denominator, we'll just end up getting this all over 1, which is itself. I'll write it out, though, just so we can see it. So that's 1, so we just end up getting 36 plus 9 radical 15. And that's it. That's the answer for this problem. But again, the more complicated part was multiplying top and bottom by the conjugate. We only do that when your denominator is this kind of two-term radical expression. With this one, I mean, the general idea is that you just multiply top and bottom by the radical of the denominator if it's just one term. But you can actually do something a little better here, which I'm going to do. Now, if you want to just multiply top and bottom by radical 26, do so and see what happens. You'll have to simplify a little bit. But what I'm going to notice is this actually can be written like this, which of course is a 1 over 13. And if you bring it back, that's the square root of 1, which is 1 over the square root of 13. So now what we need to do to rationalize is multiply top and bottom by radical 13. Radical 13 times radical 13 is radical 13 squared, much like we got radical 15 squared was just 15. This will be 13 in the denominator. 1 times radical 13 is radical 13. So we get that. And in fact, maybe just kind of showing you this kind of idea helps. If you have 1 over radical a, this always rationalizes as radical a over a. And you can kind of see that pretty simply. Multiply top and bottom by radical a, you'll get radical a squared, which is just a on the bottom, and then a radical a times 1, which is radical a on the top. So that I think kind of helps. I mean, specifically with this last part here, we can just jump to that if we recognize that. Okay, this one is a little more like specific, but it's a very similar idea. But we want to multiply by the radical in the denominator, which is only radical 5. So we multiply top and bottom by the radical in the denominator, radical 5. Okay, we'll have to distribute this here. So we get 3 radical 5 for the first term, minus a radical 5 times radical 2 is radical 10. So it's 2 on the outside and radical 10 on the inside. In the denominator, we get 3 times radical 5 times radical 5 is just 5, like it's radical 5 squared. You can also see it as radical 25, which is 5. Right, square root of 25 is 5. So this is just 3 times 5, which is 15. So in fact, we can write this as 3 radical 5 minus 2 radical 10 all over 15. And that's the final answer for this part. That concludes 7. Now let's move on to 8. All right, so now for number 8, solving radical equations. Fantastic. Now, radical equations are pretty simple, honestly. Like, the process is pretty simple. Basically, what we want to do is take both sides to the index power of whatever the radical is. So index of the radical. Like, for example, the index here is 2, 3, and 2. So we want to square both sides here, cube both sides here, and square both sides here. But the way you want to do it is you want to get the radical by itself first, and then go from there. Now, sometimes you have cases where you have more than one radical, so you may need to do it twice, isolate one of them, do it, and repeat it, and repeat the process possibly. But there's no repeats here. There's only one radical in this one, or one radical in this one, and one radical in this one. Also, sometimes when you have a variable outside of the radical, you'll get a possible scenario where you may have an extraneous solution. That also doesn't happen with any of these. Now, as it turns out, there are no extraneous solutions here, but in general, when you have a radical equation, you can check if there's an extraneous solution by plugging it in and just seeing if it works or not. But I'll tell you right now, if you have an even index radical equals a positive number, there will never be an extraneous solution. If you have a variable on the outside, like imagine this was plus x, we don't know what x could be. If x can drop this whole side down to a negative, then that would be extraneous, because a radical is never negative unless there's a negative in front of it already. So just kind of keep that in mind. Now, as it turns out, it doesn't happen here. That also won't actually happen on the exam for this class, but for number 3, that is, exam number 3, that's what I'm trying to say. So I wouldn't really worry about it too much, but I'm just kind of mentioning what could possibly happen out in the wild. So I want to isolate the radical, take both sides to the power of the index, and solve. So the index here is 2, so I'm going to take both sides to the second power. Okay, great. So these cancel. 25 squared is actually 625, so we end up getting that x minus 4 is equal to 625, and then adding this 4 to the other side will give me that x is equal to 629. There we go. And again, you can check this by plugging it in, but 629 minus 4 is 625, and the square root of that is indeed 25. So that checks out. There's no extraneous solution there. Okay. Now, I kind of mentioned even index radicals when I mentioned the extraneous solution thing. Cube root equations never really have extraneous solutions. And that's because the cube root can be negative. Like the cube root of negative 8 is negative 2, and that's because negative 2 to the third power, negative 2 times negative 2 times negative 2 is negative. It's negative 8. But since even powers can never result in negatives unless the instead was imaginary or something like that, then it can only result in a positive value. But for odd powers or odd indices, you can have negatives. Anyways, here let's take both sides to the third power. That to the third equals this to the third. Here they cancel. So we just get the inside here. 2n squared, plus 13n plus 7 is equal to 4 to the third we saw before is 64. I'm going to subtract this 64 to this side. It combines with this 7, so I'll write it below that. Let's see, 64 minus 7 is 57, so this is going to be 2n squared plus 13n minus 57 equals 0. Looks really weird. We could try the AC method and try to go from there. 57 actually does factor. It factors as 3 times 19. And what I think we could do is just try to guess and check this instead of doing the AC method, which you can do, but AC method is going to be a little hard because I'll just write it out to show you. 2 times 57 is 114, so negative 114. So we have to look for two numbers and multiply to that and add to 13. Now there is actually a way of making it work out, but I just kind of want to think about it. So again, this is 13 times 19, or 3 times 19, excuse me. So either it's in this order or in the other order, and we don't know the signs either. But notice when you multiply these, you get 3 and 38. 3 and 38 are too far apart to combine to 13, so I think the opposite order should work. 19 and 3. I notice 3 times 2n is 6n, and 19 minus 6n, 19n minus 6n is 13n. So if this is positive, that's negative, that'll happen. So that's how it factors. Now again, if you wanted to try the AC method, what'll work is looking at 114, just to kind of show you, you can write it as 1 times itself, like barely have space here, 2 times, divided by 2 you get, 57 of course, 3 times, again, 57 is 3 times 19, so you'll have 2 times 19 left over, which is 38. 4 doesn't work, so I'm not going to write 4. 5 doesn't work. 6 works, because you can divide 38 by 2. So if you imagine like 2 times 19, but 3 times 2 is 6, so that's 6 times 19. And you can actually keep trying to go down the list, but you'll eventually hit a repeat. And that's generally what happens with these. If you try to write it as 1 times itself, 2 times something, 3 times something, and keep going down, once you get a repeat, so eventually we'll go down and get another 19 times 6, but that's exactly this one. So you're going to keep going until you get a repeat. So anyways, at this point, since we're multiplying to a negative, we want these things to have different signs. So I want to look for two numbers that will subtract to this. So I'm going to take the difference of these two in any order, but I'll just do bigger minus smaller. So 114 minus 1 is 113, which is way too large. 57 minus 2 is 55. 38 minus 3 is 35. And 19 minus 6 is 13. So there we go. We wanted 13, so the numbers that work are 6 and 19. The signs that make it work are positive 19, negative 6. And remember that trick I showed you? You draw a line through this and write the square term without the square, 2n, and reduce them. This doesn't reduce, so we get 2n plus 19. And I'm not going to write it, but this reduces to n over negative 3, which is n minus 3. So it's kind of nice. And this idea, by the way, to generate the unique pair factors, this always works. So this guarantees you to find two numbers that will either add or subtract to whatever you're trying to find, provided it actually works out, obviously. I'm going to write a minus up here just to remind us that I'm subtracting these two. And again, I knew to do that because the sign was negative, meaning these will actually have opposite signs. So we're really subtracting these numbers, not adding them. Okay. So, but anyways, now that we have this times that equals 0, then by the zero product property, we just set each of the factors equal to 0. So either that's 0, in which case n is equal to negative 19 over 2, or this is 0, in which case n is equal to positive 3. Now if that was too fast, and you didn't quite like that, that's okay. You can just set them each equal to 0. If you said this equal to 0, you'll have to subtract 19, then divide by 2, you'll get negative 19 over 2. If this is 0, add 3 to the other side, you get n is equal to 3. So that's how I got that. I just did it kind of quick. And I'm calling that the zero product property, or what I call ZPP for short. You don't necessarily need to know that, but it's just the fact that if A times B is equal to 0, then this means either A is 0 or B is 0. That's all we're using here. So this is what I call the zero product property. Okay. And now this one, again, I want to square both sides, but I want to get the radical by itself first. Pretty simple. Just add 2 to both sides. We get the radical is equal to 2 minus 1 is 1. Then the index here is 2, so I'm going to square both sides here. The square and the radical cancel, so we get x minus 3 is 1 squared, which of course is just 1. Add 3 to the other side, and we get x is equal to 4. Now again, it's best to check this. And notice, when x is 4, we get 4 minus 3 is 1. The square root of 1 is 1, and 1 minus 2 is negative 1. So it works out. Great. I didn't check these, but chances are if it's a cube root, again, those generally don't have extraneous solutions. But it's still not a bad idea to check. In fact, what's kind of interesting here, I mean, it's not obvious, but I think this actually factors. Well, it's something I don't want to really look into, but let me just say that if you plug in 3, you get 3 squared is 9, times 2 is 18, 3 times 13 is 39, 39 plus, well, let's do it like this, 39 plus 7 is 46, 46 plus that 18 is, 64. Yeah, 18 plus 46, yeah, 18 plus 46, sorry, it's hard to do in my head, but 18 plus 46 is 64, and the cube root of 64 is 4. So that works. I'm not going to try this one, but if you plug in negative 19 over 2, it'll work out, surprisingly enough. Okay, so that's it for number 8. Let's move on to number 9 now. All right, number 9. It's asking us to find these operations, to perform these operations, but of course to write our answer as a plus bi. So it's a standard form for a complex number. So a complex number is a number of the form a plus bi, where a and b are real numbers. So like, for example, 3 minus 2i, which b in this case would be negative 2, so it's 3 plus negative 2i. So it's just a number plus a number times I. Now those numbers don't have to be integers like they are here. They could be fractions, they could be weird irrational radical-like numbers. So you could have like 2 plus radical 2 times I, for example. But regardless, it's a real number plus a real number times I. Now what is I? I is the square root of negative 1. Well, kind of. I is often thought to be the solution to the equation x squared plus 1 equals 0. Or x squared is equal to negative 1. So in other words, I is a number such that its square is negative 1. Now no real number satisfies this, so it's not a real number. It's what is called the imaginary unit. And any number multiplied to I is known as an imaginary number. So 2i, 6i, 7i, 4i, 5i, those are all imaginary numbers. But a complex number is a real number added to an imaginary number. So kind of something to keep in mind. Now, from our standpoint, from what we saw with radical expressions, it's the same idea because technically this is a radical, right? This kind of implies that I is somewhat the square root of negative 1, kind of. So we're going to treat it as such. In fact, really this is just combining like terms, foiling, and then here this kind of involves rationalizing. So the same ideas we saw with radical expressions, but now with just this new notation for I for this particular radical type expression, a radical type number. So let's distribute this negative. So we get 3 minus 2, minus 4 minus 6i. Let's combine like terms here. 3 minus 4 is negative 1. And then negative 2i minus 6i is negative 8i. And that's it. It's pretty simple. Now, negative 1 is a and negative 8 is b. So these are known as the real and imaginary parts of these numbers. So this is the real part. I'm just going to write RE for real part. And negative 8 is the imaginary part. Not negative 8i, just the negative 8 is the imaginary part. I don't think we quite need to know that. That's just kind of a additional bit of vocabulary, but that's as far as I'm going to take that. Now here we're going to FOIL. So that's this times this times that. So let's do that first. So 2 times 5 is 10. Okay, no surprise there so far. 2 times 7 is 14, but there's an I, so it's 14I. Good. Okay, negative 4 times 5 is negative 20, so it's negative 20I. And finally, these last two, negative 4 times positive 7, is negative 28. But notice they both have I, and I times I is I squared. Okay, but what's I squared? It's negative 1. So these two combine at the same time, so we get 10 plus, well, 14 minus 20 is actually negative 6, so it's actually going to be minus 6I. And then minus 28 times negative 1, because I squared is a negative 1. And notice here, negative times negative is positive, so we end up getting 10 minus 6I plus 28 actually, and these now combine to 38. So this is actually 38 minus 6I. So the real part of this complex number is 38, and the imaginary part is actually negative 6. How funny is that? Okay, great. So now for this one, I mentioned there's kind of some rationalizing. So I may have kind of made it look a little confusing by writing it as division, but this doesn't actually help us. I'm going to write it as a fraction. As a fraction, that actually helps us. Now you may look at this and think, okay, we can factor out the 5. That I don't think is actually very beneficial. There may be some connection there, but it doesn't actually really help to factor the 5 out. What I want to do is rationalize this. Now why do I want to do that? Because we want to get it in this form, a plus bi. And we'll see that when we rationalize the denominator, it breaks free of the radical. It's a difference of squares. And it'll actually just be a real number, and then we can split whatever the top is as whatever, the number plus a number times I is. We can split it up into an actual number plus a number times I. You'll see what I mean, but let's do it. So the conjugate of 2 minus I is actually 2 plus I. Remember, it's just a middle sign change. We have to multiply this to the entire top, so keep that in mind. Okay. Now let's talk about the denominator for a second. Now the denominator will actually combine into a difference of squares, because remember, it's a minus b times a plus b. Let me make that look a little more straight. Okay. So we get 2 squared minus I squared. If we recall that a minus b times a plus b is a squared minus b squared. So that's how I got this. Okay. Now 2 squared is 4, and I squared is negative 1. So I'll write this here. We end up with 4 minus negative 1, which is 4 plus 1, so it's actually 5. Okay, the denominator is 5. Now the numerator, I'm going to take time actually following this out. We get 20 plus 10i. Okay, 10i. Okay, and then 5i squared, so plus 5i squared. Now remember, 5i squared is negative 1, so this term is really negative 5. I hope you can see that. Not too hard, right? I squared is negative 1, times 5 is negative 5. It was positive, so it's negative now. Okay, these two combine to 20i, and these two combine to 15. Right? 20 minus 5 is 15, and 10i plus 10i is 20i. So we get 15 plus 20i. And that denominator really is 5. So this is really 15 plus 20i all over 5. And now what I was saying is that this will actually always happen. Okay? What always happens is that when you multiply top and bottom by the conjugate of the denominator, you get a real number. So the top will be some complex number over some real number. We can split it up as the real part over 5 plus the imaginary part over 5. Over whatever the denominator is in general. Now the reason why we can do this, if you haven't seen this before, this is just splitting up a fraction. Remember that the way you combine fractions that have the same denominator is by adding the numerators over that same denominator. So I'm using that idea in reverse to split up this fraction into 2. Now why that's useful here is because, well, they reduce, notice, but even if they didn't reduce, this would be our answer, because it's technically already a plus bi. But in this case, they do reduce, and you get 3 plus 4i. Great. Awesome. So that's the final answer for this one, and now let's move on to number 10. All right, so for number 10, finally, we made it. I'm asking you to evaluate or simplify these. Now, I actually use the word evaluate, but evaluate really means actually to plug in a value and then figure out what the value is. But I guess we can kind of use that term here because we're figuring out what the actual value of this is, kind of. But that's a little misleading. Really, I should say simplify, I think. But again, that's kind of being technical. So what we're going to do is we're going to look and notice, first off, these are powers of I. So let's just talk real quickly about simple powers of I. And what powers even mean is just repeated multiplication. So notice if we do I to the 1, that's just I itself. I to the 2 is I times I, but we actually know that by definition this is -1. We saw that earlier. I to the 3rd is going to be I times I times I. But remember, I times I is I squared, and I squared is -1. So in fact, this is just -1 times I, which ends up being -I. So funny enough, I cubed is -I. Okay. I to the 4th, well again, I to the 4th is I times I times I, so there's 4 of them. But 2 of them are I squared each. So you have I squared times I squared, which is -1 times -1, which is +1. So I squared is -1, that squared, which is I to the 4th, is +1 because -1 squared is +1. So I mean, that makes sense, but it's funny. And what's even funnier is that if you were to multiply both sides by I, you get the next one, which is I to the 5th. But notice how 1 times I is I. So in fact, if you were to multiply by I to get I to the 5th, you find out that it's equal to this. And you're kind of back and stuck in this loop. So in fact, every power of 10 is either I, -I, negative, or -1, -I, or +1. And in fact, really a quick way of doing these is just to notice the remainder when dividing the power by 4. So in fact, I can write a theorem here that I to any power is equal to I to the r, where r is the remainder of the division n divided by 4. Now why that is because it kind of has to do with this this kind of cyclic repetition pattern of powers of I. And you kind of think about it for a moment, and the more you think about it, the more different ways you try to do it, the more this will make sense. So maybe I'll just try to explain that if we were to write it out, we get I times I times I times I, so there's 10 of them. Which you could do it this way, but this is a pretty horrible way of doing it. Let me try to count here. So I have 9 so far, so there we go. Now, every 2 i's, that's I squared. Okay, and that's -1. So this is -1 multiplied by itself a bunch of times. And in fact, notice, any even power of I is going to be either -1 or +1 from this idea. Right, you go 1, 2, 3, 4, 5, 6, 7, 8. So any even one is always going to fall at -1 or 1. And that's clearly true because if you have an even amount of i's, you can group them up into pairs, and every pair of I is just -1 because I times I is -1. So you have a bunch of -1s multiplied, which, depending how many there are, is either -1 or +1. Okay, but another way of seeing this is actually you can break it up into 4s instead of into 2s. Because into 4s you get 1, because into pairs you get -1s, but into 4s you just get 1s, and 1 times anything is itself. So notice what we end up with here is just I times I, which is I squared. So that's -1. But notice from the theorem, if you were to divide 10 by 4, well, 4 goes into 10 twice, which is 4 times 2 is 8, and the difference between 8 and 10 is 2, so the remainder of that division is 2. So in fact, this is just I to the 2nd, which is -1. 25 divided by 4 actually has a remainder of 1. You can also think of subtracting 4 from the power. So like, for example, if you subtract 4, you get 6. Subtract 4 again, you get 2. So the remainder is 2. If you subtract 4 from this, you get 21, then 17, then it takes a while. So then 13, then 9, then 5, and then 1. So this is actually equal to I to the 1, which is just, of course, I. So again, a lot of weird, funny ways of doing this. If you want to write it out, I times I times I, and every time you have 4 of them grouped together, just throw that away because it's 1, because I to the 4th is 1. You can do that, but this is really the power of kind of skipping that a little bit. Because when you're doing that, what you'll have left over, the amount of i's you'll have left over, is exactly the remainder when dividing by 4. So again, the more you think about it, the more this idea and this idea are actually the same. So just kind of keep that in mind. Now this is a little different because you have a negative power, but it really kind of actually is the same though. Because if you don't recall, negative powers just mean reciprocals. So x to the negative n is 1 over x to the n, so I to the negative 12 is 1 over I to the 12. But notice I to the 12th is actually 1. Why is that? It's because, well, there's a few ways of actually seeing that. I guess a really nice way of seeing that is that I to the 12th is I to the 4th to the 3rd. But I to the 4th is 1, and 1 to the 3rd is 1. But if you think of it from this standpoint, dividing 12 by 4 gives you a remainder of 0 because 12 is actually a multiple of 4. That's why we're allowed to do this kind of trick and write it as 1 to a power, which is just 1. So the answer here actually is just 1. Now, if you get like something like 1 over I, then you have to multiply top and bottom by I. That's kind of like rationalizing a little bit. And then you can kind of go from there. But in fact, with negatives, this idea actually works as well. So if you were to go kind of beyond in this direction, I to the 0, anything to the 0 is 1. I to the negative 1 is actually negative I. Now again, that's not super obvious at first glance, but it's 1 over I. And if you multiply top and bottom by I, you get I over I squared, which is negative 1, so that is indeed negative I. But notice the pattern still. I, negative 1, negative I, 1. So if you kind of group this chunk and repeat it up here, you have I and negative 1 right before this I. So yeah, the pattern still holds. So something to kind of keep in mind. It's kind of interesting, right? At least to me, I think it is. Now, this last one, it's not obvious what's going to happen, but I want to FOIL this out, kind of. I want to notice when we try to FOIL it out, we'll have this 1 minus I multiplied by itself 4 times. And what I'm inclined to do is group them into 2's. And I remember that if you have a binomial squared, right, like a plus b all squared, that's the first one squared plus 2 times their product plus the last one squared. So this guy, maybe I should have written these below. It's okay. Is the first one squared, 1. 2 times their product is going to be negative I doubled, so that's negative 2I. And the last one squared is positive I squared, because negative I times negative I is a positive I squared. So plus I squared. But notice, what's I squared? It's negative 1, and that cancels with this. So in fact, you just get negative 2I, and this will also be negative 2I. So in total, we get negative 2I times negative 2I, which is positive 4I squared, which is just negative 4 because I squared is negative 1, and negative 1 times 4 is negative 4. Okay, fantastic. So that concludes number 10, and it concludes the review. Really hope you all enjoyed this. I hope it helped. I know it was a little complicated. There are some things that were maybe like way harder or easier than others, obviously. But that's what I have to say. I hope it helps. I wish you luck all in the exam, and I'll see you for the next review.